In the early 1990s, 8 human beings locked themselves inside a 3-acre, hermetically sealed glass terrarium in the American desert. It was the most ambitious enclosed ecological system ever constructed, a miniature Earth designed to sustain human life indefinitely. It was an engineering triumph, and it collapsed almost immediately. Within 18 months, the oxygen levels plummeted to the suffocating equivalent of standing at an altitude of 15,000 feet. The pollinating insects went extinct. The artificial ocean became dangerously acidic, but the most terrifying failure was entirely invisible, a ghost in the mathematics. The structural concrete holding the facility together while curing was quietly absorbing the oxygen the crew needed to survive. A microscopic chemical reaction, unforeseen by the brightest minds on the planet, slowly suffocated the inhabitants. They began to starve. They turned on each other, and they were only a few miles from a bustling highway. Now take that cascading failure and isolate it. Strip away the desert, the glass ceiling, and the safety net of a breathable world just outside the airlock. Replace it with the absolute freezing void of the interstellar medium. We harbor this enduring romantic vision of the generation ship. We imagine a colossal, shining arc, slipping silently through the cosmic dark, carrying the seed of humanity to a distant, fertile exoplanet. We picture vast, rotating cylinders of hydroponic forests, gleaming metallic corridors, and dozens of generations living and dying in a peaceful, purposeful transit. We see a society passing the torch of civilization down through the centuries, an elegant bridge across the stars. But physics, biology, and the sheer scale of the cosmos do not care about our romantic visions. The void is aggressively hostile to order. A generation ship is not a voyage. It is a slow-motion, desperate war against entropy. It is an isolated island of thermodynamics where every single breath taken, every drop of water recycled, and every microscopic vibration of the hull must be accounted for and perfectly balanced for thousands of years. In a truly closed system drifting through the abyss, you are not fighting hostile alien species or navigating cinematic wormholes. You are fighting the inescapable decay of matter. You are fighting the relentless bombardment of high-energy cosmic rays that slowly degrade the atomic structure of titanium and steel over millennia. You are fighting the biological reality of a genetic bottleneck where the mutations of a few thousand isolated individuals compound in the dark. You are fighting the psychological terror of a society born into a metal box, knowing that the stars outside their viewport will not noticeably change position in their lifetime, nor in their children's lifetime, nor in their grandchildren's. The fundamental challenge of interstellar travel is not propulsion. It is not about how fast we can push a mass out of our solar system. The terrifying equation that haunts the minds of aerospace engineers and evolutionary biologists is a simple, unforgiving matter of endurance against the void. If you seek the truth in the cold dark, and if you are prepared to confront the ruthless mechanics of our universe, subscribe and join us on this journey. Our entire intuition regarding distance, survival, and the passage of time is a planetary illusion. We have spent hundreds of thousands of years evolving on the surface of a massive open biological engine. We are accustomed to breathing air that is continuously scrubbed by global weather systems, drinking water purified by the immense thermal heat of a nearby star, and walking on soil that is infinitely recycled by tectonic and microbial forces. Because we have mastered terrestrial travel, moving from continent to continent in hours, we mistakenly project this mastery onto the cosmos. We look up at the night sky and perceive a static, silent canvas, assuming that reaching the stars is simply a matter of building a faster engine and packing enough provisions. This assumption is not merely incorrect, it is a fatal misunderstanding of the fundamental laws of reality. To dismantle this intuition, we must first look at the terrifying mechanics of velocity and the sheer crushing scale of the void. We imagine distance as something that can be conquered by acceleration. Currently, humanity's farthest emissary is the Voyager spacecraft, launched in the late 1970s. It is tearing through the dark at over 38,000 miles per hour, a speed that feels incomprehensible to the human mind. Yet, if Voyager were pointed directly at Proxima Centauri, the closest star to our solar system, the journey would consume over 70,000 years. 70 millennia. That is a span of time stretching back further than the dawn of agriculture, further than the oldest known cave paintings. To cross that abyss within a time frame that a human society could even conceptually track requires moving at a significant fraction of the speed of light. But here our intuition fails us again. We imagine the space between stars as a pristine, frictionless vacuum, an empty highway where a ship can coast indefinitely once it reaches its cruising speed. The reality is that the interstellar medium is not empty. It is a diffuse, invisible storm of hydrogen atoms, stray plasma, and microscopic grains of silicate dust. While the density is unimaginably low, sometimes averaging just a single atom per cubic centimeter, the staggering volume of space crossed over centuries means these collisions accumulate with devastating force. The mathematics of kinetic energy reveal a merciless truth. The destructive power of an object does not increase linearly with its speed, it squares itself. A microscopic grain of interstellar dust, no larger than a red blood cell, sitting motionless in the void, seems harmless. But when a generation ship slams into that grain of dust at 10% of the speed of light, the physics change from a gentle collision into a violent, high-energy detonation. The impact does not merely scratch the hull. It releases the kinetic equivalent of a heavy artillery shell, instantly vaporizing the dust and carving microscopic craters into the ship's armor, transforming the solid metal into superheated plasma. A ship traveling between stars is not sailing an empty ocean. It is flying blindly through an infinite, invisible minefield, where the friction of the universe itself is trying to sandblast the vessel down to its atomic foundations. Over hundreds of years, this unrelenting bombardment forces engineers to add massive, heavy shielding, layers of ice or composite metals, which exponentially increases the mass of the ship, which in turn requires exponentially more fuel to move, creating a mathematical paradox of mass and momentum that cannot be simply engineered away. Beyond the mechanical friction of the universe, there is the inescapable prison of thermodynamics. We instinctively think of a spaceship as a high-tech machine that can be turned on and left to run. We assume that with advanced enough solar panels or fusion reactors, energy can be perfectly managed. In the early 19th century, an engineer named Nicolas Léonard Sadi-Carnot was studying the limits of steam engines when he stumbled upon a terrifying, universal principle. He realized that no machine could ever be perfectly efficient. Some fraction of energy is always lost to the environment as waste heat. Decades later, this realization was formalized by physicists like Lord Kelvin into the second law of thermodynamics, establishing the concept of entropy. Entropy is the cold, unavoidable reality that in any isolated system, order inevitably decays into chaos. A generation ship drifting in deep space is the ultimate, terrifyingly isolated system. Once the propulsion systems shut down and the centuries-long coasting phase begins, the ship becomes an artificial island of order, plunging through a realm of absolute zero. Every single action aboard the vessel accelerates its decay. Every time a human being exhales a breath of carbon dioxide, every time a water pump circulates fluid through the hydroponic bays, every time an artificial light flickers to feed the crops, a microscopic fraction of usable energy is irrevocably converted into waste heat. This heat cannot simply vanish. In the vacuum of space, there is no air to carry the heat away. A vacuum is not cold. It is an incredibly effective thermal insulator. The ship must actively pump this waste heat into massive external radiators, bleeding its thermal potential out into the dark. It is a slow, multi-generational hemorrhage of energy. No matter how perfectly the closed-loop life support systems are designed, you cannot recycle energy with absolute perfection. Over a journey of 1,000 years, the relentless mathematics of entropy ensure that the ship is slowly, mathematically dying from the moment it leaves orbit. And then we must confront the biological arrogance of our intuition. We assume that because humans are adaptable, a crew placed inside a large enough metallic cylinder will simply continue to reproduce, farm and survive as they would on Earth. But biology is not a static blueprint. It is a chaotic, evolving chemical reaction that relies on massive, open planetary systems to remain stable. In the mid-20th century, ecologists and population geneticists began to map the mathematical thresholds for extinction. They established brutal ratios to calculate the minimum viable population needed to keep a species alive in isolation. If a population is too small, a phenomenon known as genetic drift takes over. Random mutations accumulate. The genetic diversity required to fight off diseases or adapt to environmental changes vanishes. To maintain a healthy human population without catastrophic inbreeding over centuries, a generation ship would need to carry tens of thousands of individuals. But an immense population requires an immense biosphere, which requires an immense ship, further compounding the kinetic and thermodynamic nightmares. Furthermore, the human crew is not the only biological factor. The ship must carry a microbiome, the invisible ecosystem of bacteria, fungi, and soil microbes necessary to break down human waste and grow food. On Earth, if a crop fails due to a fungal infection, we have an entire planet of alternative ecosystems to draw from. Inside the steel walls of a generation ship, the biological feedback loops are terrifyingly short and fragile. A single aggressive mutation in the bacterial scrubbers, or a fast-spreading blight in the agricultural bays, would sweep through the ship in weeks. There is no external supply chain. There is no fresh soil to import. If the fragile equilibrium of the onboard ecosystem tips too far in any direction, the resulting famine or atmospheric toxicity is irreversible. Finally, our intuition fundamentally miscalculates the sociological weight of deep time. We assume that purpose is something that can be seamlessly inherited. We imagine the original crew embarking with a heroic sense of duty, understanding that they will die in the dark so their descendants can see a new sun. But human psychology does not operate on geological timescales. By the fourth or fifth generation, Earth is no longer a memory. It is a myth. It is a fairy tale told in grainy videos in the ship's archives. The individuals born into the metal corridors of the ship have never felt the wind, never seen an ocean, never looked up at a sky that isn't made of steel and artificial lights. They are born entirely adapted to a localized, enclosed reality. To them, the ship is the entire universe. The destination, an exoplanet thousands of years in the future, is a completely abstract concept that has absolutely no bearing on their daily survival. The intense psychological pressure of living in a confined space, governed by strict rationing, absolute authoritarian maintenance protocols, and the claustrophobic knowledge that there is no escape, breeds a terrifying social friction. We expect humans to act as rational guardians of a multi-millennial mission, yet human history is defined by factionalism, ideological schisms, and conflict over scarce resources. In a closed ecosystem, where every calorie and every molecule of oxygen is heavily taxed, an ideological dispute does not lead to a political debate. It leads to sabotage, civil war, and the catastrophic failure of the delicate thermodynamic balance, keeping the void at bay. To understand the sheer paralyzing scale of the mystery, we must first abandon the comforting fiction of a static universe. When we look up from the surface of our world, the constellations appear as permanent fixtures, frozen in a silent, eternal geometry. But this is merely an optical illusion born of our unimaginably short lifespans. The galaxy is a violent, churning vortex. Everything is in a state of continuous, chaotic motion. The stars are not painted on a ceiling. They are massive, volatile spheres of thermonuclear fire hurling through the dark at tens of thousands of miles per hour. Imagine aiming a rifle at a target. Now imagine the target is an insect, flying erratically through a hurricane thousands of miles away. Now imagine that the bullet you are firing will take 50,000 years to reach its destination. This is the staggering mathematical nightmare of astrogation. You cannot simply point a generation ship at where a star is today. You must aim at where the mathematics predict the star will be tens of millennia from now. But calculating this trajectory requires accounting for the gravitational pull of every single celestial body. The ship will pass along the way. In astrophysics, calculating the gravitational interaction between two bodies is beautifully simple. But the moment you add a third or a fourth or a billion shifting stars, the mathematics collapse into an unsolvable chaotic system known as the n-body problem. The equations tell us that even a microscopic error in our initial calculations, a misjudgment of velocity by a fraction of a millimeter per second, will compound over deep time. 1,000 years into the journey, that microscopic error blossoms into a deviation of millions of miles. The ship would drift silently past its destination, missing the target entirely, plunging forward into the endless, empty dark, with no fuel left to turn around. And even if the navigation is miraculously flawless, we must confront the horrifying reality of what we are actually aiming at. Humanity currently searches for habitable exoplanets, using magnificent instruments, capturing the faintest whispers of ancient light. We use a technique called transit photometry, staring unblinking at a distant star, waiting for a microscopic dip in its brightness. That temporary shadow tells us a planet has crossed its face. From that shadow, we attempt to deduce the mass, the orbit, and perhaps the chemical composition of a world we cannot even truly see. But there is a devastating trap hidden in the physics of light. The speed of light is the absolute speed limit of reality, and because of this, the universe functions with a crippling, inescapable latency. It is much like the latency of a global computer network, where the information you receive is always slightly out of date, but magnified to a cosmic, terrifying scale. When we observe a star system 100 light-years away, we are not seeing it as it is today. We are seeing a ghost. We are looking at a photograph taken a century ago. The light we analyze has spent lifetimes crawling across the void, dodging nebulae and gravitational wells, just to reach our lenses. This means a generation ship is essentially sailing blind toward a phantom. By the time a multi-generational voyage crosses the abyss and finally decelerates into the target system, tens of thousands of years will have passed. The planetary system they arrive at may be radically, violently different from the one their ancestors observed through a telescope. A world that appeared to have liquid oceans and a stable atmosphere could have undergone a catastrophic runaway greenhouse effect, transforming into a boiling hellscape of sulfuric acid. The parent star could have entered an unstable phase, sterilizing the system with relentless barrages of X-ray flares. The crew, separated from Earth by an insurmountable ocean of time and distance, would arrive at their promised land only to find a charred, dead rock. This brings us to the closest available candidate, the most likely destination for a desperate human exodus. Sitting just over 4 light-years away is Proxima Centauri, a red dwarf star that hosts a roughly Earth-sized planet in its habitable zone. But the term habitable is a cruel clinical categorization. It simply means the ambient temperature might allow water to remain liquid. It says nothing about survival. Proxima Centauri is not like our Sun. It is a dim, violent, and highly unstable dwarf star. Because it is so cold, its habitable zone is pulled extremely close to the star itself. And in the unforgiving mechanics of orbital physics, when a planet orbits too close to its host star, the immense gravitational tides act like invisible brakes on the planet's rotation. Eventually, the planet's rotation locks into sync with its orbit. This terrifying phenomenon is known as tidal locking. One side of the planet is permanently fixed, facing the thermonuclear fire of the star, baking in an eternal, blistering, shadowless day. The other side is plunged into permanent, freezing, apocalyptic night. If a generation ship arrived at a tidally locked world, the descendants of humanity would not find a welcoming Earth. They would find a world of extremes, where the only theoretical sanctuary is the Terminator line, a razor-thin twilight ribbon of perpetual dusk separating the boiling hemisphere from the frozen wasteland. But the mathematics of atmospheric dynamics suggest that this twilight zone would not be peaceful. The staggering temperature differential between the two hemispheres would drive global supersonic hurricane winds that would scour the surface without end. And worse still, red dwarfs are notoriously tempestuous. They routinely unleash colossal stellar flares, sudden eruptions of magnetic energy that can strip away a planet's atmosphere entirely. The destination is not a paradise, it is a planetary torture chamber. Yet before the ship even reaches this nightmare, it must survive the journey. The space between the stars is referred to as the interstellar medium. We often visualize this as a pure, flawless vacuum. It is not. It is a sprawling, invisible ocean of scattered debris. We are currently protected by the heliosphere, a massive magnetic bubble generated by our Sun that deflects the worst of the galactic weather. The moment a generation ship crosses the heliopause, leaving the sun's domain, it enters the true unprotected wilderness of the Milky Way. This wilderness is filled with microscopic grains of silicate, carbon, and ice. On Earth, driving a car through a thick fog merely coats the windshield in moisture. But a generation ship must travel at least 10 or 20% of the speed of light to reach another star within any manageable time frame. At these relativistic speeds, the physics of collision shift from mundane to apocalyptic. The kinetic energy equation dictates that the destructive power of an impact is tied squarely to its velocity. A grain of sand drifting motionless in the dark holds virtually no energy. But when an armored spacecraft violently forces its way through that grain of sand at 37,000 miles per second, the impact is catastrophic. The sand grain does not bounce off. The sheer velocity forces the atoms of the sand and the atoms of the ship's hull to interpenetrate, releasing a massive flash of kinetic energy. The microscopic impact site instantly superheats, vaporizing the metal and creating a localized explosion of plasma. Imagine standing on a battlefield in complete darkness while a silent, invisible machine gun fires 1 billion rounds a second at the walls of your bunker for 1,000 years. This is the reality of relativistic travel. The ship is constantly, endlessly sandblasted by the universe. Engineers propose brilliant solutions, such as deploying a massive shield of solid ice or layered composite armor ahead of the ship. But this introduces a brutal paradox. Shielding requires immense mass. The heavier the ship, the more fuel is required to accelerate it, and more fuel requires larger tanks, which adds more mass, which requires even more fuel. The mathematics spiral into a recursive nightmare, a trap where the sheer weight of survival makes the journey physically impossible to start. Even if we solve the mass paradox, we run headfirst into a vastly more insidious killer. Kinetic dust is a physical object that can theoretically be blocked, but the void is also saturated with galactic cosmic rays. The name is misleading. These are not rays of light, they are physical pieces of atomic shrapnel. When a massive star dies, it detonates in a supernova, an explosion so incomprehensibly violent that it outshines entire galaxies. The shockwave from this death shatters the atoms in the surrounding space, stripping away their electrons and violently accelerating the bare, naked nuclei across the cosmos at nearly the speed of light. These are galactic cosmic rays. They are heavy, invisible bullets, atoms of iron, carbon, and oxygen, traveling with the kinetic energy of a fast-moving baseball, compressed into a space smaller than a single human cell. These particles are the apex predators of the deep dark. They do not merely hit the hull of a ship, they pass straight through it. When a high-energy iron nucleus tears through a human body, it acts like a microscopic wrecking ball. It violently severs the delicate spiraling ladders of human DNA. On Earth, our thick atmosphere and strong magnetic field catch and absorb this shrapnel, creating the beautiful ghostly glow of the auroras. In deep space, there is no atmosphere. The hull of the ship is the only defense. But here, the laws of physics execute a cruel, terrifying irony. When you place heavy, dense shielding between a human crew and the incoming cosmic rays, you do not solve the problem. You make it worse. When a cosmic ray hits a thick plate of lead or steel at near light speed, it shatters the atoms of the metal itself. This impact triggers a cascading subatomic explosion, a shower of secondary radiation. The metal shielding absorbs the primary bullet, but in doing so it fragments, spraying the interior of the ship with a deadly mist of neutrons and gamma rays. The crew would be trapped inside a vessel where the very walls designed to protect them are glowing with induced lethal radiation. This continuous subatomic bombardment does not kill instantly. It is a slow, multi-generational execution. Over decades, the accumulation of microscopic genetic damage begins to unravel the crew. Cancer rates skyrocket. Cognitive decline accelerates. But the true horror manifests in the womb, as the DNA of the isolated population is continuously shredded and incorrectly repaired. The error rate in cellular division compounds. The original crew might survive, but their children and their children's children will inherit a severely degraded genome. Without the protective embrace of a planetary atmosphere, the very blueprint of humanity slowly rots in the dark. And the cosmic rays do not only attack biological tissue, they are equally ruthless to technology. A generation ship must rely on highly sophisticated computer systems to manage the thermodynamic balance, navigate the celestial drift, and maintain the agricultural bays. These computers operate using microscopic transistors, pathways of electrons so incredibly small that a single high-energy cosmic ray passing through a processor can physically alter a data bit, flipping a 0 to a 1. This is known as a single event upset. On Earth, these are incredibly rare anomalies. In deep space, they are a continuous, relentless barrage. If the ship's artificial intelligence relies on a complex web of algorithms to keep the engines firing and the air breathable, a corrupted memory bank is a death sentence. The crew would not even know they were in danger. They would simply wake up one morning to find the atmospheric scrubbers venting oxygen into the void, or the navigation thrusters firing randomly, throwing the massive vessel into an irrecoverable spin. The latency of space means there is no mission control to call for a software patch. There is no backup server. The ship is a fragile island of logic, plunging through an ocean of chaotic, destructive energy. We are left staring at an abyss where every fundamental force of nature seems perfectly calibrated to annihilate human existence. The stars drift away from our calculations. The light we follow is an ancient lie. The destination is a hostile, frozen rock baking in radiation, and the path between is an invisible minefield of relativistic shrapnel that slowly dissolves the mind, the body, and the machinery of survival. When we attempt to engineer our way out of this radiation-soaked microscopic minefield, we slam face first into an invisible, insurmountable wall. It is not a barrier of steel or stone, but a barrier constructed entirely of mathematics. To understand why a generation ship cannot simply outrun its own decay, we must return to a cold winter in rural Russia at the very end of the 19th century. There, a reclusive, deaf schoolteacher named Konstantin Tsiolkovsky sat at his desk, staring at the foundational laws of motion, and quietly derived a formula that would become the ultimate tyrant of human spaceflight. He calculated the exact relationship between the mass of a rocket, the speed of its exhaust, and the velocity it could ultimately achieve. The mathematics he uncovered are brutally, uncompromisingly cruel. It is known today as the ideal rocket equation, and it dictates a recursive, compounding nightmare. To move a massive object through the void, you must expel mass in the opposite direction. This requires fuel, but fuel itself has mass. Therefore, to carry the fuel required to move the ship, you must add more fuel to push the original fuel. And to push that secondary fuel, you must add a tertiary layer of fuel. The mathematics do not scale linearly, they scale exponentially. The equation reveals that to accelerate a heavy generation ship to even 10% of the speed of light using any form of conventional chemical propulsion, you would require a fuel tank significantly larger than the entire observable universe. Even if we upgrade our ambitions to hypothetical nuclear fusion engines, the efficiency gains barely dent the tyrannical curve of Tsiolkovsky's math. The ship becomes a colossal, flying gas tank, where the payload, the human crew, the hydroponic forests, the shielding, represents less than a fraction of a percent of the total mass. The universe imposes an exponential tax on momentum, and it is a tax that standard physics cannot afford to pay. Faced with this mathematical dead end, theoretical physicists and aerospace engineers are forced into the extreme margins of reality. They look for the absolute limit of energy density to cheat the rocket equation. They look to antimatter. In the realm of theoretical physics, the collision between a particle of matter and its antimatter counterpart is the holy grail of thermodynamics. Unlike nuclear fusion, which only converts a tiny fraction of its mass into energy, a matter-antimatter annihilation is 100% efficient. It is the complete and instantaneous conversion of physical mass into pure, unadulterated kinetic energy. On paper, an antimatter engine solves the mass paradox. You would only need a few thousand tons of antihydrogen to push a city-sized arc across the stars. But this elegant mathematical solution masks a terrifying, fatal paradox of engineering. Antimatter cannot exist in contact with our universe. The moment a single atom of antihydrogen touches the normal matter of the ship's hull, it detonates. Therefore, you cannot store this fuel in a tank. You must suspend it in a perfect, frictionless vacuum, held perfectly in place by an intricate web of extreme magnetic and electric fields, known as a penning trap. This magnetic bottle must remain absolutely stable. And here, the paradox closes its jaws. Generating those immense magnetic fields requires massive amounts of power. The ship must constantly consume energy just to keep its fuel from destroying it. If the power grid flickers for a fraction of a millisecond, if a microscopic vibration disrupts the superconducting coils, or if a rogue cosmic ray from the interstellar medium pierces the containment computer and flips a single 0 to a 1 in the software, the magnetic field blinks. In that microscopic fraction of a second, the antimatter touches the walls of the containment vessel. The resulting explosion would not just damage the ship, it would unleash the concentrated energy of a small sun inside the engineering bay. The generation ship would evaporate into a cloud of highly radioactive plasma before the crew's nervous systems could even register the flash. The paradox is absolute. The only fuel dense enough to physically move the ship is the one guaranteed to completely annihilate it at the first microscopic failure over a 1,000-year journey. Desperate to escape the tyranny of mass and the suicidal danger of antimatter, theorists have attempted to circumvent motion entirely. In the mid-1990s, a physicist named Miguel Alcubierre looked deeply into the complex tensors of Albert Einstein's general relativity and found a loophole. Einstein proved that space itself is not an empty stage, it is a flexible, dynamic fabric. Alcubierre proved mathematically that you do not need to push a ship through space. Instead, you can compress the space directly in front of the ship and expand the space directly behind it. The ship sits entirely motionless inside a localized bubble of flat spacetime, while reality itself moves around it, carrying the vessel forward like a surfer on a gravitational wave. The math of the warp drive is flawless. It perfectly balances the equations of relativity. Yet when we attempt to translate this beautiful geometry into physical engineering, it violently collides with the bedrock of quantum mechanics. To bend spacetime in the manner Alcubierre proposed, the universe demands a material with negative mass. It requires a form of exotic matter that falls upward, that actively repels gravity, possessing a negative energy density. In the microscopic world of quantum field theory, looking at the phantom fluctuations of empty space in phenomena like the Casimir effect, negative energy briefly whispers into existence. But to scale this microscopic ghost up to macroscopic proportions, to wrap an entire generation ship in a shell of negative mass, violates the fundamental energy conditions of the universe. Even if an advanced civilization could somehow synthesize this impossible material, the physics of the warp bubble create a localized apocalypse. As the bubble sweeps through the interstellar medium, sweeping up stray hydrogen atoms and cosmic dust, it accelerates these particles to extreme ultra-relativistic speeds along its leading edge. The moment the ship arrives at its destination and drops out of warp, all of that accumulated, highly energized matter is unleashed forward in a devastating shockwave of Hawking radiation and gamma rays. The ship would arrive only to instantly sterilize the very planetary system it intended to colonize. The universe fiercely protects its speed limits, and the penalty for breaking them is mutually assured destruction. If we cannot bend space, and we cannot safely harness antimatter, we are forced back into the slow, agonizing reality of the multi-millennial drift. We are forced to rely on the sheer, brute force endurance of solid-state physics and materials science. And here we encounter the macroscopic breakdown. Materials science is fundamentally the study of atomic bonds. Steel, titanium, ceramics, and carbon nanotubes are all, at their core, just billions of atoms holding onto each other in the dark. We view these materials as permanent, unyielding structures, but on a geological timescale, metal is a remarkably fluid, mortal thing. Over hundreds of years, these atomic bonds experience invisible, relentless fatigue. The generation ship is a massive, vibrating thermodynamic engine. The constant thermal expansion and contraction as the ship rotates to distribute heat, the microscopic, ceaseless vibrations of the life support pumps, the subtle gravitational tides of passing rogue planets, All of this injects stress into the hull. Microfractures begin to form deep within the crystalline structure of the titanium bulkheads. On Earth, this is not a terminal problem. We melt down degraded infrastructure, purify the metals in massive industrial smelters, and forge new beams. But metallurgy in a closed, isolated ecosystem is a thermodynamic impossibility. The extreme heat required to smelt and reforge heavy metals would consume vast amounts of the ship's strictly rationed energy reserves, while simultaneously flooding the interior atmosphere with deadly, unmanageable waste heat. You cannot simply build a heavy industrial foundry inside a delicate, sealed terrarium. Consequently, the ship cannot truly repair its macroscopic skeleton. It can only patch it. Over millennia, the crew would be forced to slowly cannibalize non-essential internal structures to reinforce the failing external hull. It is a terrifying, slow-motion amputation of the vessel. The architecture of their survival slowly shrinks, creating a claustrophobic trap where the physical world around them is visibly, mathematically dissolving. But the most fragile component of the ship is not the titanium hull, the atmospheric scrubbers, or even the biology of the crew. The most terrifying vulnerability is the physics of memory. A generation ship must carry the entire cumulative knowledge of human civilization. It must store the complex astronomical algorithms required to navigate the chaotic n-body problem of the galaxy. It must hold the architectural blueprints of the ship's internal systems, the genetic sequences of Earth's biology, and the agonizingly precise instructions on how to actually decelerate and establish a colony when they finally arrive. How do you store thousands of petabytes of critical data for 100 centuries in a high-radiation environment? Our current civilization relies on solid-state drives, magnetic platters, and optical media. These are astonishing technological achievements, but they are incredibly temporary artifacts. Data is not abstract, it is profoundly physical. On a hard drive, information is stored by manipulating the microscopic magnetic polarization of tiny metallic domains. But the universe leans toward entropy. Left alone, the ambient thermal energy of the environment, combined with the relentless background radiation of deep space, slowly causes these magnetic domains to flip back to a neutral state. On a solid-state drive, information is held by trapping microscopic pools of electrons within microscopic silicon gates. Over decades, those electrons physically leak through the insulating layers in a process known as quantum tunneling. This inevitable decay is called bit rot. Over a journey of thousands of years, the digital archives of the generation ship will slowly, quietly dissolve into randomized static. Algorithms will become corrupted. Life support blueprints will become unreadable. You could attempt to solve this by engraving the data into physical plates of gold or tungsten. But the sheer astronomical volume of data required to run a starship, to reboot a biosphere, and to cure complex genetic diseases cannot be physically etched into metal without adding hundreds of thousands of tons of dead weight to the ship, which immediately triggers the rocket equation paradox once again. This creates the most haunting scenario of the entire endeavor. A generation ship could miraculously survive the kinetic bombardment of the void. The massive bulkheads could hold against the vacuum. The delicate agricultural bays could sustain the descendants of humanity. The ship could arrive perfectly positioned in the orbit of a distant exoplanet. But the central computers, heavily degraded by centuries of bit rot and cosmic ray impacts, would have lost the encrypted instructions on how to initialize the deceleration sequence. The descendants born into a metal world they do not understand would sit in the command center of a godlike machine, possessing absolutely no memory of how to operate it, watching silently as their promised world flies past the viewport, lost forever into the endless dark. And even if the computers remember, we must confront the final, fatal mechanical trap: the physics of stopping. We obsess over the immense energy required to achieve incredible speeds to cross the void, but we suffer from a profound planetary bias regarding deceleration. On Earth, when you want to stop a vehicle, you apply brakes, transferring kinetic energy into heat through the friction of the road and the resistance of the atmosphere. In the perfect, frictionless vacuum of deep space, there is nothing to push against. The void will not slow you down. To stop a generation ship traveling at a fraction of the speed of light, you must exert the exact same staggering amount of energy it took to accelerate it in the first place. You must physically rotate the entire colossal structure of the ship, point your primary exhaust directly along your line of travel, and fire the main engines as a massive brake. But recall the inescapable tyranny of the Tsiolkovsky equation. To have fuel available at the end of the journey to slow down, you must have carried the immense mass of that specific fuel for the entire 10,000-year transit, which means you needed exponentially more fuel at the very beginning just to push the fuel you were saving to stop. This recursive trap effectively doubles or triples the impossible mass requirements of the ship. Mission planners, staring at this insurmountable mathematical wall, propose desperate theoretical workarounds. They theorize deploying a magnetic sail, a microscopic web of ultra-thin superconducting wires, cast out hundreds of miles ahead of the ship, attempting to catch the incredibly faint stream of protons emitted by the destination star. The idea is to use the alien star's own solar wind as a gentle, multi-decade brake, but when we apply the models of tensile strength to this concept, the physics shatter. The structural tension exerted on a web of wires thinner than a human hair, as it attempts to absorb the immense relativistic momentum of millions of tons of incredibly fast-moving mass, creates forces that currently tear apart the molecular bonds of any known material. The universe, in its cold and indifferent mechanics, will gladly allow a generation ship to coast forward into the silent dark forever, but it demands an impossible apocalyptic toll to allow it to stop. If the universe will not allow us to stop, and if the void violently rejects our passage, we are forced to confront a terrifying, paradigm-shifting realization. We are not explorers waiting for an inevitable technological breakthrough. We are inmates in a cosmic quarantine. The insurmountable mathematical walls of the rocket equation, the lethal subatomic shrapnel of the interstellar medium, and the inescapable decay of thermodynamics are not engineering hurdles. They are the absolute physical bars of a cell. This realization violently reshapes our understanding of the universe and elegantly, albeit horrifyingly, solves the most profound mystery in modern astronomy. For decades, we have pointed our radio telescopes at the dense, star-choked heart of the Milky Way, listening for the faint, organized whisper of an alien civilization. We have mapped thousands of exoplanets, calculated the billions of habitable zones, and applied the Drake equation, which mathematically suggests our galaxy should be teeming with intelligent life, echoing with the digital chatter of sprawling interstellar empires. Yet there is only absolute deafening silence. This terrifying contradiction is known as the Fermi paradox. We have desperately invented theories to explain this silence. We assume that perhaps intelligence is exceedingly rare, or that civilizations inevitably destroy themselves with nuclear fire or artificial intelligence before they can reach the stars. But the physics of the generation ship reveal a much colder, much simpler truth. The Great Filter is not a sudden cataclysmic event. It is the distance itself. The universe does not need to actively exterminate intelligent life. It simply isolates it to death. Every civilization, no matter how profoundly advanced, no matter how biologically resilient, wakes up on their native world and looks up at the same stars, bound by the exact same laws of physics. They discover the same fatal equations. They realize that crossing the abyss requires energy outputs that shatter matter, and that surviving the transit requires shielding that makes the journey impossible to begin. The great silence of the cosmos is not an empty graveyard. It is a vast uncrossable ocean, filled with billions of isolated islands, each hosting a brilliant trapped civilization, all screaming into the dark, entirely unable to reach one another. We are all marooned by mathematics. When we strip away the comforting illusion of a glorious interstellar manifest destiny, the hidden consequences for our own species crash down upon us with suffocating weight. If we cannot leave this solar system, our entire perspective of the future, of progress, and of our ultimate legacy collapses inward. Our entire civilization, from our economic systems to our art, is built upon the unspoken foundational assumption of infinite tomorrows. We unconsciously believe that even if we destroy this planet, humanity will simply pack its bags, board a fleet of silver ships, and begin again under a new, pristine sun. But if the stars are forever locked away, the Earth is no longer a temporary cradle. It is the only lifeboat we will ever have, and it is a lifeboat with a rapidly approaching, non-negotiable expiration date. We possess a dangerous, widely accepted misconception about the end of the world. We are taught that we have roughly 5 billion years before our sun exhausts its primary hydrogen fuel, swells into a monstrous red giant, and physically engulfs the inner planets, incinerating the Earth. 5 billion years is an unimaginable span of time, a time frame so vast it grants us psychological amnesty. It feels like eternity. But astrophysics tells a vastly different, far more urgent story. The death of the Earth will not begin in 5 billion years. The catastrophic unraveling of our biosphere is scheduled to commence in less than 1 billion years, a mere fraction of the time life has already existed on this rock. To understand our true localized doom, we must look at the nuclear furnace of the Sun. As our star furiously fuses hydrogen into helium deep within its core, that newly created helium ash does not simply float away. It is incredibly dense, and it slowly accumulates at the center. As the core becomes heavier and denser, its immense gravity pulls the surrounding layers of hydrogen inward, crushing them with ever-increasing pressure. This immense pressure acts as a catalyst, slowly and steadily increasing the rate of thermonuclear fusion. The Sun is not burning at a constant, stable rate. It is mathematically accelerating. Every 100 million years, the Sun's luminosity, its raw energy output, increases by roughly 1%. This sounds like a microscopic margin, a statistical rounding error, but a planetary biosphere is an agonizingly fragile, heavily leveraged thermodynamic balancing act. In roughly 800 million years, the increased solar radiation bombarding the Earth will force the global temperature past a fatal, irreversible threshold. This will not instantly boil the oceans, but it will trigger a microscopic cascading catastrophe in the chemistry of the atmosphere. As the surface temperature rises, the rate of evaporation accelerates, filling the lower atmosphere with vast quantities of water vapor. Water vapor is a potent greenhouse gas, which traps even more heat, accelerating the cycle. But the true executioner is a geological process called silicate weathering. As the hotter, wetter atmosphere interacts with the rocky crust of the Earth, carbon dioxide is scrubbed from the air and bound into minerals, washing into the oceans and becoming trapped in the tectonic plates. Currently, this process is balanced by volcanoes venting carbon back into the sky. But under the punishing heat of the brightening sun, the weathering process will accelerate exponentially, pulling carbon dioxide out of the air much faster than the Earth can replace it. Carbon dioxide is the absolute foundation of the planetary food web. It is the breath of the flora. Within a few 100 million years, the atmospheric carbon dioxide levels will plummet below the minimum threshold required for C4 photosynthesis. In a geological blink of an eye, the global forests, the sprawling grasslands, and the microscopic phytoplankton in the oceans will suffocate and die. This is not a theoretical model, it is a rigid chemical certainty. When the plant life dies, the production of atmospheric oxygen ceases immediately. The herbivores starve, followed rapidly by the carnivores. The ozone layer, created by the interplay of oxygen and sunlight, will dissipate, allowing lethal, unfiltered ultraviolet radiation to sterilize the surface of the planet. Shortly after, the oceans will cross their boiling point, evaporating entirely into the atmosphere, creating a runaway greenhouse effect that will transform the Earth into a pressurized, barren hellscape indistinguishable from Venus. We are not at the beginning of Earth's habitable epoch. We are living at the very end of it. The biological window is slamming shut. If the stars are a physical impossibility, and our homeworld is quietly marching toward a chemical apocalypse, humanity's only remaining option is a desperate, localized retreat. We must migrate outward within the confines of our own solar system, always running from the expanding, terrifying heat of the dying sun. We will be forced to colonize the dead, frozen environments of Mars, the irradiated icy moons of Jupiter, and eventually the pitch-black, frozen methane shores of Titan. But this is not a glorious expansion. It is a multi-millennial, strategic retreat into increasingly hostile bunkers. Building a civilization on a frozen moon in the outer solar system is merely building a generation ship that happens to be tethered to a rock. You are still trapped in an entirely artificial, closed thermodynamic loop. You are still entirely dependent on failing nuclear reactors for heat and artificial light for crops. You are still fighting the relentless, crushing reality of entropy in an isolated system. Furthermore, as humanity spreads across the vast distances of the solar system, we will violently confront the physics of divergence. We assume that a human born on Earth, a human born in a pressurized trench on Mars, and a human born under the global ice sheets of Europa will all remain fundamentally human. But biology is incredibly plastic, and evolution does not stop simply because we possess technology. The gravitational constant on Mars is only 38% of Earth's. On the moons of Jupiter, it is even less. The radiation environments are radically different. The absolute lack of natural sunlight alters the circadian rhythms, the chemistry of the brain, and the development of the skeletal structure. To survive in these brutal, disparate environments, humanity will be forced to embrace extreme, aggressive genetic engineering or heavy cybernetic integration. Over the span of 10,000 years, the localized populations will adapt, mutate, and change to fit their specific, terrifying habitats. The vast distances between these planetary colonies will introduce a crushing communication latency, shattering any unified human culture. A message from a colony in the Kuiper Belt to a colony on Mars will take hours to arrive, and physical travel will take years, requiring immense, resource-heavy orbital maneuvers. The human species will not remain a unified, singular entity. It will fracture. We will splinter into a dozen grotesque, highly specialized subspecies that can no longer interbreed, can barely communicate, and share nothing but a distant, mythical, and long-dead homeworld. We will become aliens to ourselves, living in isolated, dark corners of a dying solar system, fiercely guarding our dwindling resources. We will watch the sun grow larger, redder, and angrier in the sky, knowing that even this desperate diaspora is only a temporary delay. Eventually, the sun will shed its outer layers, expanding all the way to the orbit of Mars, before collapsing into a cold, dense white dwarf. The solar system will go dark forever. This is the hidden, paralyzing consequence of the generation ship paradox. The inability to cross the interstellar void means that our history is strictly confined to a single, localized theater. It means that all of our ancient wars, all of our breathtaking art, all of our scientific triumphs, and all of our agonizing suffering are trapped inside a microscopic, slowly failing terrarium. We cannot spread our legacy across the galaxy to ensure its survival. We are forced to realize that the human story, despite its brilliance and its violence, has a definitive, non-negotiable ending. We have always defined our species by our horizons. For thousands of years, we looked across vast, uncharted oceans and saw continents waiting to be mapped. We looked at the moon and saw a stepping stone. We looked at the glittering tapestry of the Milky Way and saw our inevitable destiny. We have built our entire modern mythology, our science fiction, and our collective hope on the arrogant assumption that the universe is an open frontier, simply waiting for us to arrive. We unconsciously believe that our ingenuity, given enough time, will eventually shatter any physical barrier placed in our path. But the cosmos is not a frontier. It is a profoundly locked door. The concept of the generation ship is the ultimate monument to human denial, a desperate mechanical prayer offered up to a universe that is completely deaf to our survival. It represents our profound, psychological inability to accept that some thresholds physically cannot be crossed, no matter how brilliantly we engineer the attempt. The terrifying laws of thermodynamics, the lethal kinetic realities of the interstellar medium, and the mathematically insurmountable walls of the ideal rocket equation are not engineering hurdles waiting to be solved by our descendants. They are the permanent, rigid architecture of reality. They are the absolute limits of the physical world. When we finally accept that we cannot leave, we are violently forced to reevaluate everything we believe about our place in the dark. We are not the protagonists of a grand, sweeping interstellar epic. We are not the seeds of a sprawling galactic empire. We are an isolated, highly improbable biological accident, clinging to the fragile, cooling crust of a dying planet, orbiting a steadily accelerating thermonuclear furnace. We are trapped inside a microscopic failing terrarium, playing out the entirety of our history, our wars, our art, and our suffering in absolute, inescapable isolation, entirely cut off from the wider mechanics of the galaxy. This realization reframes the night sky. The great silence we hear when we listen to the stars with our colossal radio arrays is no longer a profound mystery. It is a terrifying mirror. It is the silent echo of billions of other brilliant trapped civilizations, all waking up on their own isolated worlds, all looking up at the same stars, and all slowly realizing the exact same horrifying truth about the tyranny of distance and mass. They are all screaming into the void, and they are all completely trapped. The universe does not hate us. The void is not an actively malicious entity trying to destroy us. It is infinitely worse. It is completely, perfectly indifferent. It operates on a spatial scale and a time scale that renders human existence mathematically irrelevant. We will continue to watch the night sky, but we will no longer view it as a map of future colonies or a promise of salvation. We will view it as a silent, infinite museum of unreachable fires. We will remain here, strictly bound by gravity, radiation, and time, living out the final, fleeting chapters of our habitable epoch. There is no escape hatch. There is no shining metallic arc, waiting to carry humanity into the deep. There is only the Earth, slowly suffocating under an aging, brightening sun, and the endless, uncrossable dark, waiting quietly to consume it all. Description. The space between stars is not an empty, frictionless highway. It is an invisible, relativistic minefield governed by brutal thermodynamics, subatomic shrapnel, and inescapable mathematical paradoxes. To build a generation ship is to declare a multi-millennial war on the fundamental laws of physics. And physics does not lose. This documentary explores the terrifying reality of interstellar travel, the fatal trap of the ideal rocket equation, the biological nightmare of deep space isolation, and the chilling reason why humanity might be permanently quarantined within a dying solar system. If you enjoy what we do here, like and subscribe. It genuinely helps. Sources: A. Ideal Rocket Equation, Glenn Research Center, https www.grc.nasa.gov, Beginners, Guide to Aeronautics, Ideal Rocket Equation. B. Hazard, Space Radiation, NASA Human Research Program, https www.nasa.gov, HRP, Hazard, Space Radiation. C. The Habitability of Proxima Centauri b, NASA Technical Reports Server, https ntrs.nasa.gov, citations 2018,3054.